So we were talking about convection, okay, and we are done with its introductory stuff where we talked about few different types of boundary layers. We just discussed few analytical solutions, and then we also talked about few correlations as well. So now we would move on to the specialized topics. Now what do I mean by specialized topics? We would specifically talk about force flow over external or you can say aerodynamic bodies, right? Spheres, cylinders. In the first instance we will talk about those bodies, and then we will talk about flow inside a pipe. How can we see heat transfer? What are the correlations or what can be the solutions for heat transfer inside a pipe? This would be the second section. And meanwhile we would be talking about the heat exchanger, flow inside a heat exchanger, what kind of thermal conditions you should consider, what should be the geometric specification. So this is just an idea, and similarly in the later part we would be talking about the natural convection as well. Okay, so in this lecture and in the next lecture I would be talking about this external force convection for external flows. Okay, and for external flows you already know that from your fluid dynamics class we kept talking about what? Flat plate flows, airfoils, cylinders, spheres. Okay, you would see that few of the correlations which I am going to show you, you have already seen that. You are already familiar with those relations. Okay, and this is just a list of topics which I am going to cover as far as that forced convection for external flow is considered. We would be talking about friction and pressure drag. You already know what flow separation is. I hope you remember the discussion on, we have extensive discussion on those topics. How can you develop a wake behind, let's say, an airfoil, behind an oscillating airfoil. I have already showed you few videos as well. Okay, and you must be remembering those videos from National Science Foundation as well. Okay, from YouTube. So this is basically the sequence of the same topic, but what is the additional thing is the additional content would be related to the heat transfer. Okay, so let me talk about the very basic stuff first, and then you would see how is it related with heat transfer and then the friction coefficient. You might be seeing these flows earlier. Okay, flow over a car, let's say an airplane, a wind turbine, a house, everything is there. All of these are examples, the flow over all these bodies. These are examples of external flows. Okay, what is an external flow? Where boundary layer can grow infinitely. What is an internal flow? Where you have an enclosed pipe, the flow is enclosed in a pipe and the boundary layer cannot be extended infinitely. So if you look at that, there are few interesting things. You might be seeing, let's say, fog coming onto the windscreen of the automobile, right? The same can happen, sorry? No, anything. All of these things are moving. So we are talking about force flows, forced convection. Similarly, there are some problems related to the icing. I am using the word icing. You might have seen it earlier. I'm sorry, where has it gone? This stuff, icing, right? It means, for example, just consider an airplane flying at an altitude of, let's say, 35,000 feet or let's say 30,000 feet. Now, those who have experienced those flights, they might have seen, you can say, different types of very cloudy environments. Okay, and due to that cloudy environment, the temperature is obviously lesser than 0 degree centigrade we can say. Okay, so the water particles, they may be in the form of ice particles at such an altitude. Okay, now just consider that if that ice is present on the wing surface and air is flowing over it, you can say that there would be some different types of aerodynamic performance if ice is developed on the wing. Like for example, if this is the simple wing, you can say there would be some friction drag over there. Obviously it would have some aerodynamic performance. If the icing is there on its surface, it would change its aerodynamic property. It would change its aerodynamic performance. Okay, and generally if you are dealing with jet engines at that height, you can consider how big a problem can it be. It would deteriorate all the aerodynamic performance, all the thrust, all the drag, or whatever it is. Okay, so power requirements can change as well. Now it means you have to do something to take care of the heat transfer so that there can be a phenomena known as de-icing. You need to get rid of that icing thing. Okay, so this is related to heat transfer. Now similarly, if you look at the building, you are going to calculate the heat transfer load in all of those buildings if you want to design, let's say, an air conditioning system for this building. Air conditioning system. You might be having a course on air conditioning in the next semester. Okay, so you would see that you would be calculating the heating loads, and all those heating loads, they would be based upon the heat generation which is being produced inside this room, isn't it? Like for example, if there are 2 ACs in this room or 3 ACs in this room, they may be insufficient if I just double the number of students over there. There would be suffocation. Okay, so all of those things should be catered for. They need to be taken care of. You have to look at, and for example, if the temperature outside this building is, for example, 5 degrees centigrade, it's fine. Those 2 ACs might work. Like if you put them at a temperature of 20 degrees centigrade or 25 degrees centigrade, they might work, right? But for example, if the temperature is, let's say, 45 degrees centigrade, which it generally occurs during summer, so they might not be performing very well. Okay, so this is the condition. You need to calculate the heating load, then you need to propose all the solutions. So this is very important. Similarly, the same thing can happen for those wind turbines as well. Okay, there can be icing stuff, there can be de-icing stuff, and a very, you can say, layman concept is, if you rub your hand just like this, you would start feeling the heat between the surfaces, isn't it? So that's a common thing, that friction is causing that heat generation. So that's how you can associate CF with Nusselt number or convection coefficient. So my point is, we are just going to talk about few of those correlations, few of those analytical relations which are used to look at the performance of the system in terms of friction coefficient and in terms of heat transfer. For friction coefficient, you already know we need to calculate CF. For heat transfer, you already know we need to calculate Nusselt number. Okay. So this is just about friction and pressure drag. I hope it is very clear to you what is the friction and what is pressure drag. You remember the example where we had this kind of plate. For example, this plate, and there is a flow coming onto it. So pressure on this side, what? This pressure would be lower than this pressure, right? So you would see that this flat plate would experience a pressure drag. But if you are talking about this horizontal flat plate, there would be no pressure drag. Why? Because this plate is very, very thin. There would be no pressure drag at all. And what would be the pressure component? Drag component. That is all due to friction. That is all due to friction. Pressure drag is what? There are 2 components of the drag. Just to continue my discussion, one component is based upon pressure and the other component is based upon, you know that, we have been talking about that stuff. Similarly, there are 2 components of lift, one due to pressure and one due to friction. Okay, so this force is generated by shear stress and this force is generated by pressure difference. Remember that. Okay, just go back, check your fluid dynamics notes. and you would have that discussion. I have put all the points on this slide just to summarize all those things. Otherwise, we have basically taken care of everything. So, my point is there are two components, pressure drag and friction drag. The only thing which I want to remind you, in case of flow over a flat plate or flow over a wing or flow over an airfoil, which component is dominant? Just look at that stuff. Is it the pressure component which is dominant in case of flow over a flat plate or an airfoil or a wing, or is it a friction? It is the shear part, which is the friction coefficient. Why? Because they are thin bodies. If they are thin bodies, pressure difference would not play any, you can say, dominant role in creating the major drag component. So if you consider that bluff body, just like a cylinder and a ball, for example, what would be the dominant component? Is it the friction part or is it the pressure part? Come on, is it the friction part or the pressure part? It is the pressure part. Why? Because it is a bluff body, and due to the bluff body, just remember that flow separation thing, there would be a loss of pressure in the wake right behind the body, and then there is an increase in pressure just because of the zero velocity thing. Just remember that discussion, try to remind it. If this is the body, what is the velocity at the leading edge? 0. What should be the pressure? You understand that? Okay. So pressure drag is dominant in case of bluff bodies. Friction drag is less dominant. But we would keep talking about both of these things. The only thing is you need to remember that in case of flow over airfoil, thin bodies, just like plates, just like wings, friction component is dominant. In case of bluff bodies, just like spheres, balls, round pipes, you might have seen those pipes which are used for transporting oil or water from one region to the other. They might be passing through the rivers and flow, and those pipes may be surrounded by the fluid outside in the river or in the stream. Okay, so that is basically creating what kind of pressure drag? What kind of drag component? Pressure drag. Pressure drag is more dominant. Okay, so you need to take care of that. So this is the point which I wanted to highlight. There is a second point. If you remember, we talked about the advantages of turbulent flows. Like for example, if you have a laminar flow and a turbulent flow, in which case you would have more heat transfer or more friction? Turbulent flow. Okay. So turbulent flows, in case of laminar flows, you would have lesser friction, you can say, lesser heat transfer. In case of turbulent flows, that friction coefficient would increase, right? And why would that friction coefficient increase? Just remember a small V component due to the production of those small eddies which we have talked about earlier. Okay, so these are few salient points which I wanted to share. This is how you define the drag coefficient. I would take the advantage of the discussion we have done earlier. Okay, not going to explain. You can consult your notes. And CL is what? And then there is an area, right? And this force is a composition of two forces. Remember that. One was due to what? Pressure, and the other one was due to shear. Okay, you have already done that. So, in case of flow over an airfoil or flow over a flat plate, you consider that area to be what? In case of flow over flat plate or airfoil, that should be the surface area. And in case of a bluff body, that is the frontal area. That is the frontal area which you see from the side, okay, from the front side. So this is just the explanation. I have put some points from the textbook because this is about the fluid dynamics, so I would skip that portion. Do you remember this figure? The flow is coming from this side. This is the ball. After a certain Reynolds number, the flow would be detached from this surface, and you would see those kind of vortices. You remember that? And you would see that this is the region where flow has been detached from the body. This is the region. So here pressure is low, right? So this is the separated region behind the body, and this is known as wake. Okay. So again, just to give you a reminder, if you have a bigger wake, would the pressure drag be low or high? If you have a bigger wake, yes, it should be high. Okay. So these are few points which needs to be remembered. Okay. Now this is something important. You already know what is friction coefficient. Okay. You remember we talked about the relation between the friction coefficient and the Nusselt number in the last chapter. You remember that? You might have seen that this was of this kind. The form of that relation was just like this. You have some constant, then you multiply it with the Reynolds number, and then you multiply it with the Prandtl number. Okay, and then Reynolds number and Prandtl number, they would have their own coefficients, exponents, powers. Okay, so those powers are experimentally determined. Those powers are experimentally determined, or you need to see those powers very carefully, you can say. So you see, this C coefficient depends on geometry and flow conditions. Okay, you would see wherever we define the relationship between Nusselt number and CF, we would have this kind of relationship. And then there is an important thing. Whenever you perform experiments, because you have seen that there are complex bodies, okay, just like flow over a plane, flow over wind turbine, flow over a house, building, whatever it is, you cannot find out an analytical solution all the time. So as far as those experimental considerations are concerned, just again giving you a reminder of that Buckingham pi theorem, you always get your results in terms of those pi products, and those pi products are what? Non-dimensional numbers. And you remember we talked about this thing, that Nusselt number, which is a non-dimensional number itself, that is dependent on x star, which is a non-dimensional x. And what is that x star? X over L, right? And this was dependent on Reynolds number, and it was dependent on Prandtl's number. Okay, and if you talk about CF, how many parameters were there? Yes, that was only dependent on x star and Reynolds number x. And if I talk about the average CF, that should be what? That should only be dependent on Reynolds number. Similarly, Nusselt number, this is the functional dependence of local Nusselt number on non-dimensional x, Reynolds number and Prandtl number. And if you take its average, it would be dependent on only Reynolds number and Prandtl number. Okay, and generally the relationship for Nusselt number, or the dependence of Nusselt number and this Prandtl number, is shown in this form. Okay, is shown in this form. So this is quite important as far as solution of the problems is concerned, or if you are designing a system or you are trying to find out some performance parameters, what temperature you need to use for properties of the fluid. Like for example, in case of a flat plate, this is Ts and this stream is at T infinity. So you, for let's say Reynolds number, you need to calculate what? Mu, rho. At what temperature you need to find that out? Film temperature. Okay, this is known as film temperature. By the way, there is an interesting thing about those relationships. You always mention along with those correlations, you always mention that at what temperature you need to find out the fluid properties. Okay, there would be correlations, not in this topic. In the next topics, you would see that there are correlations where you need to find out the values, fluid properties, values of the fluid properties at some other temperature values. Okay, so just be very careful about the temperature at which you need to find out fluid properties for a certain application. So this is known as film temperature. Or there is another thing. An alternative way of accounting for variation of properties with temperature is to evaluate all the properties at free stream temperatures and multiply the Nusselt number by this or this. This is very interesting again. One thing, you find out fluid properties at film temperature, solve the system, let's say for Nusselt number using those correlations, that's fine. But for example, you don't have the table and you just remember the values at free stream temperature, that is 25 degrees centigrade or 20 degrees centigrade. You know the values at that temperature. What you can do is you can solve this complete system using those values at free stream temperature, and then you can multiply that Nusselt number value with what? This thing, Prandtl number infinity by Prandtl number surface. Prandtl number determined at surface temperature, Prandtl number determined at, right? But there is again a thing that if you want to find out Prandtl number at surface temperature, you would have to go back to that quantity. Okay, so this is just an alternate if you want to use it, no problem at all. So this is the point. Either you go for that film temperature or this alternate. Both of those things would give you, you can say, acceptable results. So this is about the friction coefficient. For laminar flow, this relation you have already seen. 4.91 x over Reynolds number x under root. You already know that. CFX, you can find that out. In the last chapter we found that. Okay. And these are the relationships for Reynolds number less than critical value. What is the critical value for a flat plate? 5 into 10 raised to power 5. And what is the critical value for a cylinder? It is 2 into 10 raised to power 5. Generally you can consider those values. As far as that textbook knowledge is concerned, you can consider those values. So for turbulent flows, you cannot solve, by the way, those relations came from the analytical solutions. You remember those Blasius profiles I talked about? Although I didn't solve the Blasius equation, but I just gave you the similarity solution, and from those similarity solutions you came out with those expressions. You cannot solve those equations, those Navier-Stokes equations for turbulent flow. So what you can do is, in any case, you have to go to the experiments, or you have to perform the numerical simulations, right? So these relationships are experimentally measured relationships. Delta is equal to 0.38 x over Reynolds number raised to power 1 by 5, and this local CF is 0.059 over Reynolds number raised to power 1 by 5, and this relationship is true for this range of Reynolds numbers. Okay. If I ask you to find out average friction coefficient, what can you do? Average friction coefficient. See, average properties. You need to integrate this CFX from 0 to L and then divide by 1 by L. Okay. If you can integrate this relationship with respect to X, then it is fine. But there are some relationships which you would see that you cannot perform the integration analytically. You cannot solve those. You have to go for the numerical integration. Have you done that numerical integration? Like for example, you can approximate the integral. You would not come up with the actual relationship for CF, but you can get the values. Numerical solutions, they just give you values, they don't give you some relationships. But anyways, luckily for this local CF, you can find that average CF. If you integrate it, divide it by L, you would come up with this relationship 1.33 over Reynolds number, complete Reynolds number raised to power 1 by 2. Similarly, for turbulent flows, if you integrate this relationship, you would come up with this one. Okay. So for example, there is a case where this is quite interesting. For example, this is a flat plate, and I ask you, obviously as you move along the plate, Reynolds number would increase. As you move along the plate, Reynolds number would increase. For example, up to this length, Reynolds number is less than 5 into 10 raised to power 5. And from this point onwards, Reynolds number is greater than 5 into 10 raised to power 5. It means this is the point where you reach the critical Reynolds number. Okay, then how would you find out the average CF? Integration in parts. You have to integrate this relationship from 0 to, let's say, I would say this is capital X. So you have to perform this integration CFX laminar, I would say, I am just putting L over there, from 0 to capital X dx, and then you have to perform the other integration from capital X to L for CFX for turbulent values. So for length from X to L, you have to use the relationship for turbulent flow, and from 0 to capital X you have to use the relationship for laminar flow. Okay, by the way, what does that mean? That up to this point you have laminar boundary layer, and after this point you would have introduced those vortices, and from here to here you may have a transition region, and then the complete boundary layer, turbulent boundary layer, can be observed. Okay, so this is important to understand, that there could be flows where you can have a considerable length for the laminar boundary layer, considerable length, right? And in that case you have to perform the integration in the form of different components. Do you understand that? Any question about this thing? Okay. Then turbulent, but you have to take care of the limits. Like for example, if these are the limits for the laminar flows, like for this length Reynolds number is less than 5 into 10 raised to power 5, then you would use, let's say, these limits for laminar relationship, and these limits for turbulent relationship, not the turbulent relationship for the turbulent flows. Sorry? No, this whole should be divided by 1 over L, no problem at all. This whole could be divided by 1 over L. Okay, anything else? Yes, this is for laminar and this is for turbulent. So this is what I have explained on the next figure. Now there is an other interesting point, that CF would not be a function of friction, surface smoothness. This CF would not be a function of surface smoothness for what kind of flows? For what kind of flows? Laminar flows. It is dependent on this surface smoothness parameter if you consider laminar flows. But this CF would be a strong function of this epsilon term, which represents that smoothness parameter of any surface, if you are considering the turbulent flow. Okay, so if you have turbulent flows over a rough surface, friction coefficient would increase to a considerable extent, and you need to consider this relationship, which was proposed by Schlichting in 1979 to find out this average CF. Okay, So you see, that's how the research papers and the textbooks are connected. This result might have been explained in some research paper at a conference, or let's say in a journal, and then it was used for the applications. Okay. And obviously from along with CF, we need to consider this laminar flow as well. These are the values for laminar flows for Nusselt number. You have seen this value. Now just remember, this is C, Reynolds number R, Prandtl number N, isn't it? This is the coefficient. This is the analytical solution, by the way. And this is the experimentally determined solution. This is turbulent flow. And these are the parameters for which those relationships can be used. This is only true for Prandtl number greater than 0.6. And by the way, we modified the relationship. You remember that? What was that? We introduced something to make it acceptable for all kinds of flows, or let's say to increase its range. What was that? There was a relationship. We name it. Yes. That was something to relate CF and Nusselt number. Okay, but still by introducing a parameter into it, I think they just multiplied Prandtl number raised to power what? 2 by 3 or what? Right, minus 1 by 3, and you can expand it. And where does that Prandtl number come from? Experiments. You have to correlate the data. Okay, you have to correlate the data. So again, this is for not time average, average Nusselt number. You just integrate it, divide it by 1 over L, you would come up with this relationship, and this is applicable for this range, and this relationship is applicable for turbulent flow, and this is just a representation of the boundary layer. You remember that CF, it decreases as you move along the plate, it decreases. Okay, and when it reaches the turbulent state, it goes to the maximum value, and then again it decreases. Okay, remember the reason which I told you. It increases. Why? Because of the introduction of the V small component, V velocity. It increases. There is a velocity, another velocity gradient component. So it increases its value, and then it starts decreasing. Why? Because as you move along this thing, partial u by partial x or partial v by partial x, they starts decreasing. The same reason. Okay. So these are the ranges for the Prandtl numbers. Understood? Any question? Okay. For liquid metals, where you have very low Prandtl numbers, you remember that Prandtl numbers are very low for liquid metals. And if Prandtl number is low, what kind of boundary layer would be dominant, or what kind of boundary layer would be thicker? So for liquid metals, where you have very low Prandtl numbers, Prandtl number less than 0.05, and this is something which is known as Peclet number. Okay, Peclet number. Peclet number is basically a combination of, or you can say a product of the Reynolds number and the Prandtl number. Right, Peclet number. This is just a new number introduced by one scientist known as Peclet. Okay, so he used that product to define his correlations. So he found out that if these are the relationships, you should go for this expression to find out Nusselt number for liquid metals over flat plates. For liquid metals over flat plates. And by the way, there are so many energy applications or heat transfer applications where you consider the flow of those liquid metals. Okay, and I would just give you a reading assignment. Just go back and check what kind of flows are associated with liquid metals. What are those heat transfer applications? Just note it. This is a reading assignment. Okay, just note it down. This is kind of a reading assignment. Just Google this thing. Okay, so people always try to expand the relationship, the range of the relationship, where they are more applicable to a wider range of parameters, right? So these are the scientists, Churchill and Ozo, a very well-known relationship in heat transfer. They proposed this relationship, where they said it is applicable for anything like that. Okay, Churchill and Ozo. Like for example, if your fluid flow is only fulfilling this condition, you can easily use this relationship. They would give you acceptable results. Okay, and while looking at those relationships, the only point is that you need to remember all of those relationships, they have been found out through experiments most of the time, and you need to find out the curve fitting on the points. You perform, let's say, experiment for Peclet number, let's say 101, and then you perform experiment for Peclet number 200, 300, 400. So you draw the data points and then you interpolate. You interpolate or you start to find out some curve which can fit all the points. Okay, you would see those kind of discussions in your numerical methods course. But my point is, you should understand this, and the only thing is, you can see there are a number of relations which are available to you through research papers, through those textbooks. You may find different relationships if you go to the book by Incropera. You may find different relationships. Okay, but my point is, you should use this one. Why? Because this is considered as a textbook for this portion of our course. Okay, otherwise you may find all of those relationships are correct, no problem at all. As long as you are fulfilling those limitations, you are considering those limitations, all the relations are giving you acceptable results. Okay, but don't make your own during the exam. Okay, so by the way, there is one more thing, that how many types of boundary conditions are there? Thermal boundary conditions. There are two boundary conditions. You can specify temperature or you can specify flux. Okay. Now those relationships are obviously dependent on the boundary condition as well. What kind of boundary condition you are using for the flat plate. Those relationships, they are generally applicable for isothermal plates. Isothermal plates. Isothermal plates means the whole plate has the same temperature. But you can also use that for non-isothermal plates. You can also use those relationships, not this one. You can also use this relationship, the Churchill and Ozo one. This relationship can be used for non-isothermal plates as well. Now what do you mean by non-isothermal? Where you can have flux condition. Where you can have flux condition, or where you can say partial T by partial X is not zero on the plate. Partial T by partial X is not zero on the plate. Okay. And again, there are some other things as well. You need to consider smooth flat plates. There should be no frictional component, this surface roughness parameter, and the free stream to be turbulent free. Now what does that mean? You should not consider the gusty kind of flow. Gusty kind of flow, where you have velocity fluctuations in the oncoming flows. Okay. Sorry? No, we will talk about those relationships again. I would talk about more relationships. But for example, what is the point when I say you can use this relationship? The point is, you can use this relationship but with a bigger value of error. Bigger value of error. Right? So I would, for example, I told you that you can, let's say you are trying to produce this curve pi1 pi2 You have some data points. What if I ask you to find out the value on this point? I can interpolate, right? Now the point is, if I interpolate this thing using this relationship, I may have a bigger error if I actually perform the experiment and find out the value. But if I use those dedicated relationships, I may have a smaller error. You understand that? So then we always try to figure out the things in terms of percentage error. We say that, okay, error can grow up to, let's say, 10% if you use this relationship. Error can grow up to, let's say, 2% if you use this relationship. Okay. So as far as this course is concerned, I'm not going to use that error percentage, but still you can use this one. Okay. Now this is very interesting. There can be few applications. Okay, I think we have, time is up. Okay, so I would start from this point onwards. Please go back and read your book and keep your fluid dynamics notes with you as well. Sorry?